morning, friends and dear students. It gives me immense pleasure to be here again for my course, Flight Mechanics. This course is related to the aeronautical students of 4th semester in Institute of Aeronautical Engineering, Hyderabad, India. So, in my today's topic, I am starting my next module, that is maneuvering performance. In this maneuvering performance, first topic is level turn performance. This is also called the steady coordinated turn. So, this I am going to discuss. As you know, my name is Dr. Yagya Dutta Dwivedi, professor from IARE Hyderabad, Department of Aeronautical Engineering. In this, I am going to cover few topics like level turn performance, important parameters of load, variation of the maximum load factor N versus airspeed in a level turn, corner velocity, maximum of the maximum load factor, then airspeed for maximum of the maximum load factor. So, in this Man Ki Baat session, I am going to discuss about something which we have covered in the previous. Just before this module, we have completed the climb performance. In the climb performance, we can see that if this is the horizon and the aircraft is flying like this, this is the velocity V and this is the gamma. So, this is called the climb angle. Climb angle, and in this we have seen the rate of climb. This is the rate of climb, VC. So, rate of climb was VC, and that is the, if this is the V, we have V sine gamma. This is the rate of climb. We have also seen the maximum rate of climb, the condition for ROC maximum. This will happen when we have the minimum drag. The velocity when we are flying the aircraft at a minimum drag condition, we will get the maximum rate of climb. If I draw the plot like this is the V and this is the P. So, if you see here, it is like this plot, and if I draw this is the, where it is tangent, this is the V minimum drag. If you fly in this, we will get the maximum range. If we fly at this, where it is horizontal tangent to this is the maximum endurance velocity. Endurance velocity. This is the point where this is V maximum endurance, and if it is a minimum drag, this is also called the maximum velocity for maximum range. These all topics which I have already covered in my previous lectures. Now we will see what is the meaning of coordinated turns, because now, as of now, whatever we have learned, it is an unaccelerated flight. Unaccelerated flight, where we have seen that m dv by dt is equal to 0, because there is no change in velocity and no acceleration. So, these things are 0. But here in this steady coordinated turn, if you see, this is our aircraft fuselage, and this is here having some phi degree. This is the phi. This is the banking angle. And in this condition, if we see, this is our horizontal tail and this is the vertical tail here. These are the wings. So, if you see here, we will have very different things. This is your front view. Here I will draw the side view of this I will draw with some different colors. So this is our wings. These are the wings. There's the tail, and this is the your vertical tail here. So, and here is the CG, and this is your horizontal. So if I take some different colors, and from here this is the thrust, and this is also the velocity vector in this same direction. We can see here that the lift is perpendicular to this. This is the lift. So if you see from here, this is the, here it is W, and the lift will be perpendicular to this. So this is your lift. This is a front view, and this you can see that here is a drag. This is the drag. So now what will be the, and this is here gamma. This is the weight W. Okay, so this W will be not now exactly the W. And if you see here another diagram, this is the center, and this is rotating or turning like this with the radius. I am not able to make the exactly circle. Okay, this is the circle, and your aircraft is here somewhere. Just I will write the one aircraft like this with wing, tail like this. So here this is the radius of this your turn, radius R, and this will experience one force of lift, that is L sine phi. So if you see here, this is the vertical and this is the phi here. So this vertical is a, and here this is the L sine phi. This will act towards the center, and this is the L cos phi. So here this lift here, this will be L cos phi, not only L. Okay, so here we can see that a very nice three-dimensional, and this W will not be W, this will be W cos gamma here. It depends upon here, because this will be here W cos gamma. So this I have given a small introduction of new, and here if you see, it is accelerated one because there is a centrifugal force, and here it will Fc will act in this direction, and this will make a rotation, and this rotation will always change the direction, and the velocity vector will be in this direction, and this velocity will be V cos gamma. This is the velocity vector in this direction. So this is the basic introduction which I have given for the turn. So turn is a accelerated flight. So turn is a accelerated flight as it is mentioned here. Now I will go for the further discussion of level turn performance for the jet aircraft. The load factor is defined as the ratio between the total lift and aircraft weight. So load factor N is equal to L by W. There are two types of maximum load factors. Maximum possible load factor produced by the engine thrust by power. That is the maximum load factor. Maximum possible load factor produced by the engine thrust by thrust or the power, and the maximum allowable load factor tolerable by the aircraft structures. So here we can see that this is the structural conditions, and this is the aerodynamics or engine propulsion condition. The maximum possible load factor for a sustained level turn is considered by the maximum engine thrust and the power. So this maximum possible load factor is to sustain in the level turn is constrained by the maximum engine thrust and the power. Next is maximum allowable load factor for a sustained level turn is constrained by the maximum structural strength. So this one is, if you pull up very high load factor, your wing may fail, your crack may develop, your some part may break. That is the issue of the structural problems. And when we talk about engine thrust, means how much we have the engine thrust. That can produce how much load factor. So for a fighter aircraft, the maximum producible load factor by the engine thrust is often greater than the maximum tolerable load factor by the aircraft structures. So if we see the aircraft structure, the fighter aircraft, their maximum possible load factor, which is produced by the thrust of the engine, or the power which is produced by the engine, which is much greater than the maximum tolerable load factor by the aircraft structures. However, for a general aviation aircraft, the maximum producible load factor by the engine is less than the maximum tolerable load factor by the aircraft. So it is depend upon which type of aircraft. If I have the fighter aircraft like Rafale, Tejas, Mirage, Sukhoi, these all aircrafts are producing maximum producible load factor from the engine thrust. Engine thrust is much more than that. But if you see about the general aviation aircraft which is used for commercial purpose, then their maximum producible load factor is quite lesser than the tolerable load factor of the aircraft structures. This I will be discussing in detail about the equations also in due course of time. I will be taking nearly 6 to 7 lectures on this maneuvering performance, in that different types of VN diagrams, then equations for all the conditions. This I will be discussing in due course of time. Important parameters of load factor. So here we have 4 important parameters are described. That is the maximum producible load factor, that is the neta maxima and maximum. Corner velocity, this we will be discussing. Corner velocity also, it is depend upon the, if we make a VN diagram, this is the 0, this is the minus, this is the plus, upside is this, downside is this. So this is the called here the corner velocity. So the velocity at this is the stall zone, this is the stall zone, this is the structural failure, this is the VNE, maximum never exceed velocity. If aircraft is reaching here, this is the point which is called the corner velocity, this and this. So but we will take this, our aircraft should be in between here. That is the best zone to fly. It should not exceed, otherwise aircraft will fail. Maximum of the maximum load factor and airspeed that corresponds to the maximum of the maximum load factor. So this we will be discussing in the following slides. First I will discuss about maximum producible load factor. So as the bank angle is increased, the magnitude of the lift L should be increased. So if you increase the bank angle phi, and you know what is the bank angle? This is the fuselage and this is your wing, in this time you don't have it. But if you make somewhat banking like this, so this is the phi. From horizontal, how much it is going left or the right. So if this is the aircraft, it is flying like this and it is rolling like this. So roll angle is called the phi, which is called the bank angle. So as the bank angle is increased, the magnitude of the lift should be increased too. So the CL is given as, we know that CL is equal to 2N, where N is a load factor, 2N W by rho V square S. As L increases, the drag due to the lift will also increase. So as it is induced drag, so drag is equal to half rho V square S CD. Half rho V square S CD, we can write, it is a total CD here. Total CD. This from the polar, drag polar, we can write that CD is equal to CD naught plus K CL square, where K is equal to 1 by pi E aspect ratio. So this is the value of the K. So here we can write that drag is equal to half rho V square S CD naught plus KCL square, which we have already seen many times. To maintain a sustained level turn, the engine thrust should be increased for cruise level. So if the drag is high, and we know that T is equal to D, so if drag is high, we need thrust also high. So thrust should be increased. So as you bank, so thrust should be increased. It means the throttle of the engine to be increased. So that is the consequences of this. So as you start your flying, as it is steady flight, lift is equal to weight, thrust is equal to drag. As you bank some 5, then what will happen? There is an increase in the drag. This increase in the drag needs increase in the thrust. From where we will get the thrust? Thrust we are going to get by increasing the throttle. It is like an accelerator in the bike. So we have the throttle on the cockpit. We have to increase the throttle. Some percentage of the throttle is increased. And as you increase, the power of or thrust of the engine will be increased. So bank angle makes sure that it is drag is increased. Due to increase in the drag, we need the more power. So we have to take care of, as we are flying in the banking zone, we have to ensure that your power of the engine has to be increased. Otherwise, it will start sinking down. So now we will see that T is equal to, thrust is equal to drag, half rho V square S, CD naught plus K. Here CL square, we have seen in this that CL is equal to this. This value we are putting here. K into CL is equal to 2N W by rho V square whole square. Solving this equation for N. So if we solve this, a very simple algebraic calculation, because here is the N, so we can write that here, that if you want to do the calculation, this we can do here. So N is equal to rho V square S, rho V square by 2 into K into W square. Here T minus half rho V square S CD naught. So T minus half rho V square CD naught, and this term will be rho V square by 2K W square. This will go below, and this will be T minus D term will be here, T minus half rho V square S CD naught. So we got this load factor. This load factor N is the function of the velocity is here. This is the velocity here. Then we have the thrust here. Then we have the density here and here. Altitude, aircraft weight, W, and the aerodynamic features. That is the CD naught and all. So the load factor is depend upon the so many factors like velocity of the aircraft, engine thrust producing or power producing, how much altitude your aircraft is flying, how much weight the aircraft has, and what are the aerodynamic characteristics like CD naught. What is the zero lift drag? These all features has to be considered. The maximum value of n is obtained by employing the maximum thrust. So how you can get the maximum n? So thrust. See, as you increase this thrust here, that much your n will increase. Having the lowest weight, because weight is here, if you have the lowest weight, your n will be increased, and flying at the lowest altitude, and your rho should be lowest. So these are the parameters which we have to see, that the aircraft which is having high thrust, having lowest weight, and flying at the lowest altitude will give the best load factor. So if we make here that weight is a minimum, thrust is a maximum, and rho naught is lowest. This is the lowest. So we fly, we will get load factor maximum. So maximum load factor n maximum is equal to whole under root rho naught v square s divided by 2k w square minimum T maximum minus 1 by 2 rho naught v square s CD naught. So this is the equation for maximum load factor. And this is depend upon the weight, minimum weight, thrust, velocity. These all parameters will make the aircraft maximum load factor will be generated. Now we will discuss the variation of the maximum load factor versus airspeed in a level term. So here we have drawn here the very important maximum producible load factor n maximum, and here in the x-axis we have the velocity. So if you see here, here this red line, it is stall point here, point A, point B, point C, point D. Then we have here all the points are here, and this is the line for the stall, and this is the n max, equation 9.45. Here n maximum, here it is n max max, thrust limit. So first we will discuss about point A in this diagram, and here is a Vn max max. This is the velocity for maximum of the maximum load factor. So point A represents maximum of the maximum load factor. This point corresponds to the velocity at which the highest bank angle can be employed. So if you are flying your aircraft at this speed, nearly 410 or so in this case, this is the velocity for maximum bank angle aircraft will achieve. This is the point. This is called point A. So this is the point A, very important. Now we will see the point B. This is the point B here. This is the point B. It is shown as 100 meter per second. Correspond to the stall speed with n is equal to 1. So when your aircraft is at the straight and the level flight, when L is equal to W, T is equal to drag, this is the straight and level flight. Straight and level flight. If you are flying the aircraft in this condition, stall speed, this is called Vs, and in this case it is 100 meter per second, or knots. It is knots. So nearly 51 meter per second speed. So point B shows it is a minimum velocity. If you fly less than this, your aircraft will go for the stall. Now you see the point C here, very important here. This is the point C. So point C is airspeed below which the load factor is constrained by stall CL max rather than the maximum engine thrust. Very, very nice. if you are flying in this speed, below this C speed means 200. So in this load factor here it is 4 in this case, constrained by stall. It is constrained by CL maximum. Aerodynamic features are here, not the engine feature. So engine feature is not matter. If you are flying here, your CL maximum, it should not exceed. Otherwise your aircraft will start falling down. Next, here is D here and D here. We have the 2 point, represents the maximum velocity with load factor 1. So if you have the load factor 1 here, and this is the velocity which you are, so for the steady and level flight where you have the load factor 1, your aircraft can fly up to this. So any aircraft, the maximum speed you will get when you are flying a steady level flight with load factor 1. That is the condition which we have to understand, that how much aircraft, how much maximum speed you can get it and which condition you can get. You can get only when your aircraft is flying a steady level flight, no turning, no banking, straight level and maintaining the same altitude. And if you are flying with a full throttle, you will get the speed which is the maximum speed. It is also called never exceed speed. Now we will discuss about the corner velocity. The corner velocity V star is defined as the airspeed below which N maximum is governed by the maximum lift coefficient rather than the maximum engine thrust. So the corner velocity is defined as the airspeed below which N max is governed by the maximum lift coefficient rather than the maximum engine thrust. So it is the speed. If you see I have shown the curve. So if you see here VN diagram, so it will go like this. 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 So this is the zone here. So this is the corner velocity. If you fly less than this, this is the speed. This is the V star. So if you fly less than this, here stall will happen. Or CL maximum is the criteria. But if you fly here, your engine thrust is the criteria. So that we have, and this area is the failure zone. This is the VNE, never exceed. These all are the danger zone. This is the stall zone. This is also stall zone. So like this is called the corner velocity. I think it is very much clear. So this CL maximum, you know that 2 CN maximum by W by rho Vs. So here CLN maximum will be less than the CL maximum. So always CLN maximum should be less than the CL maximum. Then only your aircraft will be flying. So N maximum is equal to rho V square S CL max by 2W, where V is less than the V star. So if you want to fly at N maximum, so your velocity here, this V should be less than the V star. So we can write down like this, that rho V square S CL maximum by 2W is equal to, this we have derived that earlier in the earlier slide. If you see, this we have derived N maximum here. So from here we will take this thing, this rho V square S CL by 2W maximum. Here CL maximum is equal to whole under root rho V square S divided by 2K W square T maximum minus half rho V square S CD naught. So here we can square it to remove this square root. This we have made the square. So rho V square S CL max over 2W whole square is equal to rho V square S by 2KW, which we have taken here. And this is removed, T maximum minus half rho V square S CD naught. So now we will see here that rho V square S CL square maximum, this we are taking from here, is equal to 2 by K T max minus half rho V square S CD naught. So this W is removed from here. So we will get here 2 by K. Now if you see here, so here K rho V square S CL maximum square is equal to 2T maximum minus this and this cancelled. So rho V square S CD naught. So we can write that rho V square S, K will go inside. So KCL square plus CD naught, this will go is equal to 2T maximum. Hence, we can find out this corner velocity V. So this V is equal to 2T maximum divided by rho S KCL square plus CD naught whole under root. So this is the corner velocity, a derivation for the corner velocity which we have done here. So maximum load factor with corner velocity. So N maximum with the corner velocity C is equal to rho V star whole square S CL maximum by 2 to W. We have to put this V star here in this to find the what is the CL maximum with the corner velocity. Next is maximum of the maximum load factor. This is first is the maximum, then maximum of the maximum load factor. So since in a level turn the aircraft drag is equal to the engine thrust, T is equal to D in a level flight, we can manipulate this as, so N is equal to L by W. We can multiply and divide by T by T. So L by W into T, we can write D, L by W, T by W, T by D. Here we can write T by W into L by D. It is a thrust to weight ratio and it is a L by D ratio. Both are very important parameters. Now load factor is equivalent to the multiplication of thrust to weight ratio and lift to drag ratio. So this load factor is the multiplication of thrust to weight ratio into lift to drag ratio. If the engine thrust remain constant at its maximum value, the producible load factor will reach its absolute maximum value. So if the engine thrust remains constant, if T is a constant at its maximum value, the producible load factor will reach its absolute maximum value. And that is called N max max when the aircraft has its maximum lift to drag ratio. So what is the meaning of maximum load factor? So here we got N is equal to T by W into L by D. T by W is mostly constant, and if we make the thrust also maximum and it is constant, so T by W will be constant. So if the engine remain constant at maximum value, the producible load factor, that is N, will reach its absolute maximum value, that is called N max max, when the aircraft has maximum lift to drag ratio. So this is the condition for that thing, that if you are putting the full throttle, aircraft is going full speed and at the highest L by D ratio, that load factor is called N max max. It is a maximum of the maximum load factor. It depends upon the load factor. It depends upon the drag to lift to drag ratio or the glide ratio L by D maximum. So if the L by D is maximum and thrust is also maximum, we can say that whatever load factor we are getting, it is the maximum of the maximum load factor. So N maximum is equal to T maximum by W L by D maximum. This is the equation 1. The aircraft maximum lift to drag ratio, that is L by D maximum, is, we know that it is 1 by 2 under root K CD naught. We have already derived this. Putting this value in equation 1 for L by D maximum, we have to put 1 by 2 under root K CD naught. So if you put here, you will get N max max is equal to T max divided by 2 into W L by D under root K CD naught. So this is the equation for N max max, and it is depend upon the CD naught and the maximum thrust of the engine. So this equation says that for a maximum load factor, thrust should be maximum and L by D should be maximum. So designers to choose more powerful engine with high L by D ratio. So that is the specific maximum of the maximum load factor. So just I want to focus something here. If we are designing the aircraft, so we have to make sure that our engine should have the more power, maximum power, and also the L by D ratio should be maximum. If you are able to make this thing, then only you will achieve the load factor which is maximum of the maximum. So next I am going to discuss about airspeed for maximum of the maximum load. So we have discussed just now the maximum of maximum load factor, and we know that V maximum will be under root T maximum by rho S CD naught. So the airspeed that corresponds to the maximum of the maximum load factor is only a function of 4 parameters, that is the rho, that is altitude, then wing area S, 0 lift drag coefficient CD naught, and the maximum engine thrust. So if you see this equation, there are the 4 terms. One is the rho. So V maximum is the function of rho, that is altitude, area S, CD naught, and T max. So these are the 4 parameters in which the airspeed corresponds to the maximum of the maximum load factor. So here, if you point A is less than the maximum speed and more than the corner speed, which is shown here. In the next, we are going to discuss about vertical maneuver performance, pull up and the pull out basics, effect of load factors, pull up and pull out in detail. Problem 4, pull down, zero gravity, and then orbital flight, free fall cruise. And these are the references which I am going to discuss. I have taken my slide from this. So Anderson JD Jr., Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. Elsby ME, Aircraft Performance, Theory and Practice, AIA Education Series. Any questions? yddwivedi@gmail.com. Please do like and subscribe. Give any comment. If you feel anywhere you need improvement, it will be always, I feel very happy if you give some comment. Please do like and subscribe. Press the bell icon. Till then, I am going to take another lecture very soon. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.